Continue talking about Mars today, and it's kind of rough. I mean, you could spend, guys definitely do spend their entire life studying Mars. Let me make this mic a little bit lower. But we're just going to talk about it for a day and a half. And then we'll turn to Venus. And then after that, we'll start looking at the outer planets, which are different again. So let's take a look at something that we were kind of looking at last time, and that's this big spec sheet for Mars compared to Earth. And what I want to focus on with you today, let's see if I can get my cursor, here it is this lower two rows. The orbital size, that's the semi-major axis, and the solar constant, capital C. And I told you last time about how a square meter solar panel facing the sun from Earth would catch about 1,367 watts for every square meter. And out at Mars, that same solar power is diluted down quite a bit. Here's the ratio. So the solar energy density out at Mars is about 0.43, 43% of what it is here on Earth. So make a note of that. Solar energy density at Mars is about 43% of what we get here on Earth. All right. So that means your solar powered devices won't work as hot, they won't, work as fast and stuff like that. Or you got to let them charge up more longer and stuff like that. And I want to, here's the same two rows of the table. These two numbers over here, I want to give you a little bit of a explanation about why they are the particular values they are. Now this column out here basically tells you that the semi-major axis of the Mars orbit is 1.524 astronomical units. And Earth's semi-major axis, of course, is exactly 1. Is that related to this dilution factor, the 43% dilution factor? Answer, yes. And here's how you can see it. Go ahead and jot down this simple quotient here. 1 divided by the semi-major axis, 1.524, quantity to the second power. That's the same as 1 divided by 2.3226, okay, approximately. I've done a little bit of rounding off. Okay, so you take 1.524 in your calculator, you hit the squared button, and you get 2.3226. And then you go 1 over that, and you get 0.4306. And that is not a coincidence. And the reason that that is not as a coincidence is that the solar energy, the light from the sun, sunlight, it's distributed over a sphere of radius 1.524 astronomical units. And the area of that is 4 pi r squared. So all those photons of sunlight are scattered, distributed over a much larger sphere. And so by the time you get out to the Mars orbit, that distribution, the dilution factor, is exactly 43%. Or in other words, 1 over the square of the radius of Mars orbit. So that's why that is the way it is. Okay, so 4 pi r squared is the basic formula for the surface of any sphere of radius r. It's a fairly simple formula, and hopefully it reminds you of the circle area, which is pi r squared. The sphere is just 4 times that. It's kind of cool. Another thing that we talked about last time was volcanoes on Earth, and this thing known as magma, or in in a monster movie on TV, Molten Lava. So magma is this hot molten rock that's stored underneath a volcano, and when the volcano blows, it tends to come blazing outward like this one. Now, I want to try another clicker question with you concerning volcanoes. So have your clicker ready, if you will. And I believe we have an exam next Thursday, a week from today. Is that correct? Does anybody have their calendar or their syllabus? Yeah. Well, in other words, a week from today, yeah. Okay, so the 11th, we'll have an exam, and you're going to need your iClicker for it. I gave an exam today, a midterm exam, for my physical science class in the morning, and they were using their iClickers and stuff. So I'll show you how all that works on exam day. It's pretty good. Question number 1 for today. Let's get to it. In addition to magma, a volcano that should be can also emit great volumes of. Go ahead and vote. "20 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, most of you chose A. That's good. A volcano will emit mostly gas. It won't emit a lot of liquid because it's so hot, right? It's under pressure. The fancy scientific term for this is outgas. All one word. OUTGAS, outgas. A volcano can outgas. And what can it outgas? A lot of CO2 and a lot of sulfur dioxide, both of which are pretty toxic. And I believe it's the case, if you've ever heard of Mount Vesuvius and the destruction of Pompeii in Italy, southern Italy, by the eruption of Mount Vesuvius, I believe that what killed all those people wasn't the ash that you see up in this cloud. See, it's kind of grayish brown. That's just smithereens of busted rock, so light that it's up there in the atmosphere. And there's also gas up there as well. But supposedly, what killed them all was the CO2 and the sulfur dioxide that came rolling down the mountainside. Because sulfur dioxide and carbon dioxide, those are heavier than air. Okay, so they'll tend to sink. And if you're up here on top of, this is Mount Etna, which is right across the straits from Pompeii and Mount Vesuvius, that noxious, or I should say poisonous gas, CO2 and sulfur dioxide, will tend to roll down the mountainside, and if you're close enough, it'll still be so concentrated, it'll asphyxiate you and kill you dead. It's also extremely hot. So in addition to depriving you of oxygen, it'll burn your lungs out. It's not very pretty, not a very pleasant way to die, I'm guessing. And we think that a lot of Earth's atmosphere is from volcanoes over the eons of time. And so a similar question can be asked, how did Mars get its atmosphere? So let's talk about Mars's atmosphere and its volcanoes. This is a picture of a fairly small volcano, Tharsis Tholis. And this one is this is a false color image, of course. The location of this relatively small volcano is, okay, this is called the Tharsis hemisphere, and then the other hemisphere is the Hellas hemisphere. And this is like a little basin. Now, there's no water. And if this were Earth, we'd think, okay, that's an ocean, and that's an ocean, and this here is a bay of the ocean. But on Mars, I mean, it looks like it could be an ocean. I mean, this looks like the Gulf of Finland a little bit up here. And, this could be like, some big delta like in Nigeria or the Nile Delta here. But there's no liquid water there. We think maybe there used to be. But anyways, Tharsis Tholus is right here. And so it's pretty tiny. Over here, Olympus Mons. And a bunch of other, here's a big row of 3 volcanoes over here. So this little baby here, there's another close-up of it. If you look at this detail up here, you might, and if you didn't know any better, you'd think, oh yeah, okay, that's where is that crater? Where's that volcanic crater? Is that Hawaii or something? Well, and here's like the edge, so is this like some volcano in a James Bond movie or what? And except for the fact that you've got craters, you might be tempted to think that, because here's one in Iceland. Look at that. It looks very similar. Very similar kind of curves. And then the interior, the cliffs, and the way that the cliffs are broken away. Now this is water in here, and it probably ices over in the winter in Iceland. But here's another one in the Sudan. So this is down in the middle of Africa, really hot part of Africa, and there's a bunch of water up here. The reason there's a bunch of water up there is because this is pretty high elevation. So if it were lower elevation, of course, in the Sudan, it would drain off or evaporate. It'd drain off into the Nile River drainage system, or maybe just evaporate. Here's a place in the United States. And this one, they've got an observatory up here. There's a little observatory. And you can see it's an old volcano. This one's not active. And then here's one out in Siberia, up in the northern, almost towards Alaska. Those islands out there. So you can see that here on Earth we have stuff that looks just like that baby on Mars. And so the stuff that we think happens here on Earth would easily or could easily have happened on Mars as well. And so, for instance, we think that the volcanoes have donated a lot of CO2 and a lot of sulfur dioxide, even hydrochloric acid, depending on the location of your volcano. A lot of water vapor as well. A lot of the volcanoes along the west coast of the Americas, so South America all the way up to North America, they tend to emit a lot of water just because of the structure of the continents and so forth. And so that kind of thing can happen on Mars, and we think that that is why Mars has the atmosphere it does now. Now, Mars is much smaller, so it can't hang on to its oxygen and the rest of its gases the way we can here on Earth. But we didn't hang on to our hydrogen. Go ahead and make a note of that. Earth's atmosphere, we couldn't hang on to hydrogen. We could not hang on to helium. I'm sure there was plenty of hydrogen, plenty of helium during the formation of Earth, but that all stuff evaporated away and transported away thermally. And most of Mars's atmosphere is the same. Can you replace this battery? So that's kind of what we're looking at here on Mars. And you can look at, they've got extremely detailed maps of Mars. There's another famous area up here on the Hellas hemisphere, up in this upper corner toward the north, a place called Nili Fosse. And it's a bunch of cliffs up there, kind of near this bay, right up here in this part of the basin. And this particular formation, Nili Fosse, has an additional atmospheric phenomenon that is important for us. Here's a close-up of it. The Nili Fosse, the Syrtis Major, Terra Sabe, what they found in this area is methane. Okay, these bright red areas here. Okay, that means that you've got 30 parts per billion of methane in the atmosphere. And what's really interesting about this is that it happens in a seasonal basis. So go ahead and make a note. Nili Fosse and so forth, that whole area, bright sources of methane gas. And it is seasonal. This is a bunch of Italians figured this out a number of years ago. CH4, that's the abbreviation, or that's the chemical formula for methane. It's a pretty simple gas. This is in the northern summer. It's in the northern hemisphere. It's up near the North Pole. And so in the summer, they get a little bit more heat. And they tend to get these bright plumes that we can observe from space at this particular location. And the interesting thing about it is some scientists think that this is not just a sign of methane escaping from rock. We think maybe this is methane being generated by some kind of life form. Okay? Now, most of you have seen pictures of cattle, cows. And the south end of a northbound cow is going to emit copious amounts of methane after they've been fed and after they digest what they've been fed. All right, so do you understand what I'm talking about? Methane, south end of a northbound cow, after they eat, methane comes out, breaks your nose, paralyzes your nose, etc. You don't want to be around. But we can, I mean, and other animals, matter of fact, humans, some in this room will emit methane occasionally, as well as other stuff. Anyway, so so that's why they think maybe that what they've seen seasonally is methane, probably from something like, if it is something that's alive, it's not cattle. It's probably stuff like bacteria, something, or algae, something really small like that. And speaking of life forms, let's talk about this little chip off the old block, ALH 84001. Many scientists think that it contains a fossilized life form. And this is a picture of it. And what they've done is they've, what do you think? Okay, let's turn it on. It's not working. Let me show you how it's done. Okay, see the big one here? See the big one there?
Yeah.
See the big one down there? Yeah, just go in there like that. Ding! All right, now I got power. All right, you'll learn. Our TA is learning. Anyway, so this is a picture of ALH 84001. Now this front face of it, you might be able to notice it looks flat, and that's because it's been sawed. A little slab of it's been sawed off. And down here you can see that this is a centimeter ruler here. So it's maybe about a handful. But it's a very valuable handful. And why is that? It's because of this thing right here. What is that? Look at that. All eyes forward. Look at that. Use your eyes now. Guys in the back, eyes forward. Get your nose out of your phone. Take a look. Yeah, take a look at this picture. Okay. Now, what does that look like? Looks like a worm, maybe. Except it's a lot smaller than a real worm, or even a microscopic, like amoeba type worm. But some people think that that's actually a fossilized life form. Question in the back. We don't know. We don't know what it is. They're still trying to figure it out. And, you know, I bet they're planning to make more cross-sectional cuts and, you know, and maybe find another one. Or maybe find two of them that are interacting or something like that. So this is the famous ALH 84001 candidate life form. And if you type in that word ALH 84001 and then the word life or living or life form, you'll see endless articles about it. It's huge scientific debate. You know, some people think it's bogus. Some people think, no, we got it. This is it. And other people are kind of metza, kind of in the middle. So it's kind of an interesting thing. At least it's interesting to think about. So this picture here is from an electron microscope. So really, really small. Okay, let's talk about Mars rovers. And we'll finish up our discussion of Mars. There have been a few rovers that we've tried to land on Mars, and they've crashed. It is not easy to land stuff on another planet. It's not easy to land stuff on Earth. I mean, they've been trying to get these SpaceX boosters to land on a platform out in the ocean or back on land somewhere, and they've finally been able to do it, but it was not easy. And trying to do the same thing on a planet, you know, 50 million miles away is tough. This is Sojourner that was landed up there in 1997. And this, it's kind of hard to see in this picture. It's got a little zapper on the front of it. This thing's about the size of a microwave oven, supposedly. Okay. And it's got a little zapper on the front. And what they do is they zap stuff with alpha radiation. So they must have like a little piece of radium in there in a lead-lined pocket, a lead-lined box, and they open the box and let some of the radiation from the radium out, and they zap a rock with it. And so when the minerals in the rock are zapped by alpha rays, they will in turn emit other forms of radiation, and those other forms of radiation are distinct element by element, and so we can analyze rocks in that manner. So it's kind of like stimulating or inducing a spectrum from each piece of rock that they bump that little thing up into. Now this one went out of business in about 1997. Here's some more. Let's take a look at Spirit and Opportunity. Spirit is bogged down and shut down, but I think Opportunity is still kind of poking along up there. Little bit bigger, little bit more solar cell area. You can see here, a little bit different locomotion system. And they're also looking at rocks and looking for signs of water, of course. And they have found abundant evidence for that. Let me go back here. Okay, so that's the Opportunity. And now we've got the Mars Science Laboratory up there, which is even bigger. The one that we first put up there were called the Viking landers, and they didn't do anything. They just stood there. They didn't move. They landed, and they analyzed the stuff right where they landed. They couldn't go 5 feet in either direction. And these things have gone miles away from their original landing spot. Here's a simulated look of Opportunity. So in other words, Opportunity took pictures of this terrain here, this red, kind of reddish-orange terrain, and then the NASA engineers superimposed, they photoshopped the picture of Opportunity into the picture, so it looks like you're standing right behind it. Curiosity landed in 2012, and that's the big one. That's this one. I remember that summer. It was pretty exciting when they got that thing. They were really paranoid about, is it going to crash? Is it going to survive? And when they got this thing really up and operating, I'll never forget it. They had this camera here. I believe it was this camera was not deployed. I mean, it was working, but it was folded down. So the first image that they got from Curiosity when it landed was one of the wheels. And everybody, they think, oh yeah, we got a wheel. And that's what they got that first day. But they knew that once they got a wheel, that as soon as they folded everything out, it was going to get a lot of good data. And so that's what it's been doing. And it's been looking for organic molecules like methane. And it's just been spectacular. All these rovers, they build them to last for, a year or 18 months or something like that. But these things have been going up there way past their supposed freshness date, their expiration date. And this one's going, it's going gang. It's going, what do they call that? Great guns. It's going great guns up there. Curiosity. And we'll be putting other stuff up there. So it's, it's pretty good. Here's do you know what this is? You know what that is? That's a 3D image. So you look at, if you have 3D specs, you could put your 3D specs on and look at this, and you'd have a sense of depth perception. Here's another one. Here's Curiosity looking back at its own tracks. So no, this is not where it's going. It's not following some other alien vehicle. It's just looking backward at where it used to be. But look at these rocks up here. I mean, these rocks, look how blue and gray they are. Do you know where we see rock like that here in the United States? Down in the Virgin Islands, the U.S. Virgin Islands. There's this stuff they call down there called blue bit, very hard igneous rock, and it's bluish green, just like this stuff. And this is kind of a false color here. It's not the true eyeball color, but it's fairly close. And that rare form of rock in St. Thomas in the Virgin Islands, it's right by the airport. Raise your hand if you've ever been down to St. Thomas. Anybody? Okay, a bunch of you. Most of you that went there probably went on an airplane, and the airplane comes in from the ocean and it lands at the airport, and then it runs out and it comes to a stop. And when you come to a stop, you're looking at those cliffs that have this color. And I've got a piece of it at home. I used to live in the Virgin Islands, and I loved all the geology down there and stuff. And I believe I have a piece of it at home somewhere. When you take off from St. Thomas, you start at the ocean end of the runway and you head right toward that cliff. And you better take off, because if you don't take off, you're going to go right into that cliff. But these big monsters, it's just amazing seeing those planes. They just lift off and they just go right over the top of that cliff like it's not even there. But they have rock that looks a little bit like this. And of course, the red rock, all the red dust and stuff, there's any number of places on Earth where you have deserts that are red. That's very common here on Earth. It's the iron. It's iron oxide, rust. The iron in the soil there, it oxidizes in the sunlight, and it Takes on a reddish color. Same thing as here. Okay, well that's where Curiosity went. Curiosity is going about its business. And let's go about our business elsewhere in the solar system. Let's take a look at Venus. Venus, here's Venus from space. And if you want to make a note in your notes, B-O-R-I-N-G. Boring, at least to look at it from space. And it's not very great shakes. I mean, compared to Earth, it's got 81.5% of the mass of Earth, and the radius is about 95% of the radius of Earth. So it's pretty close to the Earth in size, in kilograms. Its density is 0.951 compared to what Earth's density is, average density. So it's like, okay, nice, good, Venus, good, fine. Ditto, just put ditto marks, Charles, men are from Mars. What does that say? Men are from Mars, women are from Venus. But, boring. Orbital size, 0.723. I mean, we're not shaking anything up. So we're a bit closer to Venus than Mars is to us. And it's, it's just like a big ditto mark in the sky until you figure out its orbital rates and its spin rate. The spin rate is very slow, and it's hard to make out because these clouds, this is clouds, this is, pole to pole, North Pole to South Pole, you have a very thick cloud layer, and so you don't see weather patterns, you don't see volcanoes from space, using an optical telescope. You just see kind of this cloud cover. So it's hard to detect rotation, but we've been able to figure it out. Venus spins once every 2,802 hours. What? Earth is 24 hours. Mars is, 24 point something? Almost 25? So that's nice. But this basically has one spin every 116.75 days. So, and it only has 224.7 days per orbit. So what would happen to Earth if we spun on our axis once every 150 days? In other words, what if the morning of the day was 40 days? Or 40 times 24 hours. And the afternoon, 40 times 24 hours. And a full day, how would that work out? 160 days, 160 24-hour periods per spin of Earth. Things would be a lot different. Just think about it. If Earth spun once every 160 days, for instance, that'd be 80 days, 80 24-hour periods at night. That'd be like living at the North Pole. But it'd be year-round for everybody. So and for Venus, it also has disastrous implications. Okay, so make a note of that in your the slow spin rate coupled with the orbital rate means that you spend an awful long time. Any given square kilometer of Venus is facing the sun for an awful long time. It's slowly turning across the face of the sun. And then that same square kilometer spends an awful long time on the night side of Venus, away from the sun, because it spins so slowly. Now, you may have read this book by C.S. Lewis called Perelandra. It's kind of a science fiction book. And it's about a guy that goes to Venus. And now this is before anybody knew anything about Venus. So it was all speculation. And so on this planet, there were floating islands of vegetation and all kinds of cool animals and, of course, adventures. And, he has to rescue somebody and all that kind of stuff. But now we know that most of this stuff is OUT. There's no floating anything. There's not any vegetation. And there's not any animals, we're pretty sure, on Venus. And what I'm about to review with you is how you can tell that none of that is ever going to ever be possible. The atmospheric pressure at the surface of Venus. Now we've sent, the Russians sent a bunch of spacecrafts to land, and a lot of them crashed and stuff, but some of them successfully landed and sent back information. Surface pressure, 92 bars. Now, Earth's surface pressure on a fair day at sea level, 1.10325 bars. Or as they say on the Weather Channel, 1,103 millibars. Okay? And so 92 bars would be 92,000 millibars. And that is a lot of pressure. So Venus is basically the same atmospheric pressure as 90 Earth atmospheres. Okay, it's pretty bad. And it's about like being 3,052 feet under the sea. Whoa. And let me see a show of hands. Raise your hand if you do free diving or just skin diving. Anybody? Okay. If you do, you in the back and you guys, what's the deepest you ever dove?
60 feet.
Whoa. How about you? 50 feet? How about you? Dude, you guys are geniuses compared to, I was going to say about 30 feet for me as far as I've ever been down. But you can dive down that way if you're free diving, or if you're snorkeling, you're breathing air. If you're doing that with scuba tanks, and then you ascend too rapidly, you can get the bends and stuff. 3,052 feet, nobody could go down that far. Unless it's a movie, some kind of a science fiction movie. There was a science fiction movie called The Abyss. Raise your hand if you've ever seen it, The Abyss. It's a kind of a cool monster movie. And it was made by, was it made by James Cameron? The same guy that made Titanic. And what's that other one he made just recently with the blue people? What? Calutron? No. Avatar. Yeah, Avatar. Yeah, Avatar. He made Avatar. So he made this movie called The Abyss, and it's got these scary monsters from the briny deep that shape water and stuff, and they come up to the surface. And but one of the guys in that has to go down to find them or something, and so they sent him down there, and he's not breathing gaseous oxygen, compressed air. He's breathing a liquid, and a liquid that has enough oxygen in it, the lungs can handle that. And so he goes way, way down to the bottom of the ocean. And of course, there's a pretty girl in it, and she has to be rescued, or somebody has to be rescued. And this guy's going down there by breathing a liquid that's oxygen rich. And apparently you can do that, but I think even 3,000 feet is pretty excessive. So that's the atmospheric pressure. Yeah, men are from Mars, women are from Venus. So Venus, yeah, all kinds of dainty, nice things, sugar and spice, everything nice. Not really. That's a pretty hostile atmospheric pressure. Surface temperature, 737 Kelvin. Oh, baby. That is like 7 times the boiling point of water. So forget about it. I mean, that's like, you don't even have an oven that is that hot. I mean, you're talking way up there in temperature. So the surface temperature, 737 Kelvin, the Soviets actually landed some stuff down there. But the problem was, they got 17 of them into the atmosphere or actually down on the surface, but they only lasted a few minutes. The total time on the surface for 17 spacecraft, 684 minutes. And you can see why. Under that kind of pressure and that kind of temperature, you're going to get zapped. And the longest that anything lasted down there on the surface of Venus before it was totally fried to a crispy crunch was 127 minutes. Okay. Now we could if we cared about Venus the way that we care about Mars, we could probably design something, like made of carbon alloy or carbon composite or something that would survive those conditions. But anyways, the Russians, they put these big, look at that thing. That thing's like a tank. It's like a Russian tank. But Venus defeated those things. It's kind of amazing to think about it. So real hot. So Venus, men are from Mars, women are from Venus. Not really. Venus is extremely hostile. It is not sugar and spice up there. Okay, we have radar images, and some of the orbiters of the Venera series took radar images. And we had an orbiter up there, I think it's actually still up there, Magellan, that took radar images. The other thing that we can do is we could take images from Earth. For instance, this image here shows the disk of the sun. Here's the north, here's the east, and the west, and the south. And these two lines here show the transit of Venus in 2 different years, June of 2012, June of 2004. And that's basically a black circle that goes across the face of the sun. Venus, I mean, when the geometry is right, Venus will come directly between the SUN and us. And as we look at it, it's kind of traveling on a little bit of a slant. But yeah, that's one of the things. And we can analyze the atmosphere, believe it or not, by looking at the spectrum of Venus and the spectrum of sunlight as it crosses the edge of the sun's disk. Right here, if we track Venus the entire way as it comes in, cuts across the boundary, and then dashes across, if we track the spectrum of Venus, we can figure out a lot of the things that are in its atmosphere. So we don't have to actually land stuff there to know what we've got. Hubble Space Telescope, all the other space telescopes, you can do the same thing. Just analyze what you got, and it's kind of an interesting, although hostile place. So it looks like this image here. It doesn't look very fancy, but if you get down and take some radar images, if you try to measure the temperature and the pressure, it's definitely an exciting place, although hostile. Let's take a look at some of the radar images. These are from your textbooks. And some of the stuff that you're looking at here are volcanoes like these things here. Okay, here's another volcano down here. And I think this is a volcano up here. And look how big this is, 100 kilometers. Okay, now here's a volcano on Earth. That's a pretty big one. It's blowing. I think this is one up in Alaska. It's ginormous to us, but no great shakes compared to what you find on Venus. Here's another crater. Some of these craters are pretty big. Look at this one. Here's the length scale over here. This is maybe a kilometer across. This one over here is 10 kilometers and more, dozens of kilometers across. So it's just a different. I mean, this is a lovely day down there in Arizona, where Meteor Crater is. But it's not a lovely day up there in Venus. Okay, water erosion. We have plenty of this on Earth. Here's the Colorado River cutting through the rock formations out there. Raise your hand if you've ever been to the Grand Canyon. Anybody? Yeah, a bunch. I've never been. I'd like to go out there. There's all kinds of really... Raise your hand if you've ever been out in the Rocky Mountains anywhere, from Arizona up to Canada. Oh, man. You know, you guys that are from Florida, you just don't know. It is another world out there. You know, I grew up in New Jersey, and when I was in high school, I dreamed of going out west. You know, go camping and fishing and skiing and hiking up in the mountains, and I eventually did that after I graduated college. But you cannot imagine what the climate is like and the size of those mountains. It takes your breath away. Or in this case, the size of this canyon. I mean, that's like a mile deep from where this picture is taken down to the bottom of that river. That's a big, that's a big river. And it's a mile down. And so if you go out there, if you ever have a chance to go out there, definitely take the chance. All right. Here's a picture from the surface of Venus. Here's this poor little Venera lander down here, trying to get through the day. Didn't make it very long, but they did get this picture. This is a figure from your textbook, 7.37. Yeah, there's problems up there on Venus, you know, and it's, you know, there's not going to ever be any case of can we terraform Venus. I mean, you know, maybe we can do a little bit of terraforming of Mars, but getting Venus to be hospitable, it's just kind of a lost cause. So it's far too hot for any kind of rain or snow on the surface. And the atmosphere itself, here's the composition. CO2, carbon dioxide, 96.5, which is one of the reasons there's so much atmospheric pressure. That's heavier than air, and the air pressure there is 90 times the air pressure of our atmosphere, 92, something like that. A little bit of nitrogen, 3.5. Sulfur dioxide, 150 parts per million. That's about 0.015%. And what they think happens up there is that occasionally in the upper atmosphere, you'll get some precipitation. You know, some water that will fall out as droplets, and it'll evaporate by the time it gets to the ground. But even if it didn't, it's pretty bad because it's acid. It's not like water. It's like sulfuric acid, supposedly. So it's a pretty bad place to be if you're any kind of human or human-based technology. There's no weather because of the slow rotation. So you're just like in a Susie Homemaker shake and bake oven, you know, for 100 days or 50 days at a time, you know, bake and bake and bake, you know, until the cows come home. And they think that this lack of weather is actually also why there's no global continental-sized tectonic plates. Now, the tectonic plates on Earth, you know, like the North American plate and the South American plate, the Caribbean plate, just kind of squeezed in between them, and the Africa, the plate we know as the continent of Africa. Those things move around, we think, on the surface of Earth like rafts floating in a lake, but not on Mars. The water vapor on Mars is vulnerable to dissociation by ultraviolet. So it's, as I said, it's a hostile environment. It's closer to the sun. So all the UV that gives you sunburn, I mean, you have to have like SPF 9000 to get through the day on Venus. If you're up on a peak above a good fraction of the atmosphere where you could catch some rays, those rays would be really, really strong. Very tough ultraviolet. So rain falls on Earth before the ultraviolet can attack it. The water vapor in the air. Venus, no way. You do not get it. And so Venus it's kind of depressing. I mean, you think about all the nasty, hostile things that are true about Venus. I mean, Mars is like you barely have anything. You're holding on to a little bit that you've got, but Venus has got plenty, and all of it bad, just about. Although there might be gold on Venus, so maybe if somebody could figure out some way to build a machine to survive the Venus atmosphere and prospect for gold, there's probably buku gold in Venus. Here are the plates of Earth. Here's Africa, South America over here, and these plates, they collide. Where they collide, there's a lot of earthquakes, like the west coast of South America, west coast of the United States. Here's Yellowstone up here. That's a hot spot. Himalayas. The Himalaya mountains over here are basically a result of the subcontinent of India right here moving north and dashing through the Indian Ocean and smashing into the Eurasian plate and raising this enormous set of mountains. But they say that the Appalachian Mountains over here on the east coast of the United States were just as tall many, many millions of years ago. Here's Australia down here. Japan's over here by itself, taking down all that punishment from earthquakes and volcanoes and stuff. It's a rough place. Anyway, that's what we got for Venus. Or that's what we don't got. That's what we haven't got for Venus. We don't have any of those kind of plates. We're pretty sure there's nothing like that. Okay, next time we're going to take a look at the outer planets. This is kind of an artist's conception. Go ahead and make a note. David Aguilar. And this is an important image because in the early solar system, we think that the sun was born as a star early on, and there was still a lot of stuff, a lot of gas and dust and little pebbles and stuff floating around out in the universe. And then there was this clear band. Now, this planet here, we think, is doing what we think Jupiter has done, and that's clear the interior solar system. And you see this clear band. And eventually, Jupiter has done all that clearing. So go ahead and make a note, David Aguilar, planet forming. And next time, what we'll do is start talking about Jupiter, Neptune, and all the outer planets. So look for some Mars and Venus homework in masteringastronomy.com. I'll try to have it up by lunchtime tomorrow. It'll be due next Tuesday. You are dismissed. Yeah.
Exams, I know they're going to be on the clicker, but I know it's obviously going to be the stuff that we're learning, but what are we going to expect for the test? Is it going to be specific stuff like the stuff that was on the tables and everything like that, or is it?
Well, if I ask you a question about the tables, I'll give you the tables. So don't worry about having to memorize any kind of numbers and stuff, except for maybe Earth, 1 astronomical unit and that kind of thing. But everything that we've talked about in lecture is fair game. So that means that your lecture notes are like your study guide.
Okay.
Okay, so if I've talked about it in lecture, that means of all the zillion things we could have talked about, this was what I think is the most important. Okay, and so you're trying to figure out, okay, thanks, Matt. I'm trying to figure out, do you savvy what's most important? Okay, and the lecture notes every day tell you what Dr. B thinks is most important. So, but you've also got homework questions, and you've also got clicker questions, and then you've got reading as well. So if I talk about it in lecture, and you find a section of the textbook to read about it, then that's good too. That's good backup.
No specific chapters we should study.
Oh well, we're doing 6, 7, 8, and 9 now.
7, 8, 9,
Yeah,
so that's the main chapter
yeah.
we should look over.
Oh no, because we've done stuff from chapter 3, 4, and 5 as well. So we got a lot of stuff, but let the lecture notes be your guide, okay? And look at the broad topics every day, and then go read about it in the textbook, all right? And if I don't talk about something, and there's lots of things I didn't talk about the Babylonians too much,
So
or the Egyptians.
So in the textbook, there's no range of what it's going to cover. It's just like the entire textbook, like from 1 to 9. So I'm trying to like find out what exactly.
Yeah, you're trying to think you're trying to think in terms of chapters and stuff, but I don't think in terms of chapters, and I don't want you to. I want you to use the book, but don't be a slave to it. Okay, so if I talk about something in lecture, that means that's what you should study. So comb through the book, get your notes organized, comb through the book, and then so take your notes and then the index of the book, and then find something in your notes, and then find where it is in the book in the index, and then back in your notes write page 207 or whatever page it is. Okay, and just do that, and then go and read that stuff, and that'll help you study. That'll make you even more solid. Okay, so because we're skipping and jumping.
Yeah.
Okay, and I'm not keeping strict records of where, because I don't think in terms of the book. I'm not doing, okay, today's chapter 6.5 and chapter 6.6 and nothing else. I think about it in different terms than that. So it's going to take a little bit of thinking for you guys to do that.
We're not going to need a Scantron because you have the clicker.
Scantron? You mean for the exam?
Yeah.
Yeah, we're going to use Scantron too.
All for reading tools.
Yeah, like my is that good?
Yeah.
Did I explain that? Okay. Yeah, so on the exam, like my midterm for my physical science today, they had 45 Scantron questions, so 45 dots, and then they had 3 clicker questions for another 5 points, 2 2-pointers, and then one 1-pointer. And so you guys will probably have something like that. Okay? All right. Did you have another question? Or was okay, good.
Got a question.
Go ahead. Yeah.
I was here on Tuesday. I did the clicker and everything. I did the right answer, but I didn't get the points for it.
Did you click today?
I did not because I was late.
Oh, and you missed the one question we had. Okay. I don't know what to tell you. There's somebody what is your name?
Teresa. Sarah.
Okay. There's a young lady in here named Vasek that is also, her clicker's not clicking. But we'll do a little mini session. Do you have your clicker with you?
Yeah.
All right, just sit down for a minute and let me take care of these guys, then we'll do a little mini session.
Is that on the?
Yeah, we're recording it. That's the BOSS. Hold on a second. Oh, no, we're not going to answer that one. Question, Jacob.
What specific Scantron do we need?
The raspberry colored one with the black UCF Pegasus logo. Okay, they sell it. Dude, I think they sell them in that vending machine right outside the back door here. I don't know, go take a look.
Yeah.
Yeah, go to SGA in the student union, you get 2 for free 2 per day, I think, something like that.
Thank you for teaching today. I'm not going to shake your hand because I have a sore throat.
Yeah, good. Yeah, and I had a sore throat over the weekend. I was dog sick over the weekend. Yeah, so we don't want to, we don't want to communicate any more of that. But anyways, yeah, go ahead.
Specific I should be studying for the exam.
Yeah. Did you hear me talking about the lecture notes
No.
just now? Yeah.
Just go with my lecture notes.
Your lecture notes are your study guide.
Okay.
Okay. So organize your lecture notes. So go back to YouTube and double check and, get them all fished up nice. And then go look through all the different topics in your lecture notes and then go dig into the index of the textbook and find out where that topic from your notes is. It's on like page 233 or something. And then write that down in your notes and then go study page 233, 234 and stuff. So do that to support the textbook is to support the lecture. Okay.
Okay, I got that.
And all right.
Thank you.
All right, good, Matt.
I was the one that emailed you that I was in the hospital for the past couple of days, so I missed the clicker points. These are all my
Yeah. We'll use this at the end of the semester if we have
yeah.
to.
Because right now I have like a 30 something.
Yeah, don't worry. You're looking at those percentages in web courses.
Yeah.
And did you see on the grades page where I say don't ever do that?
No, I didn't.
Yeah, it's down at the bottom.
Okay.
Yeah, don't. I hate those percentages in web courses because they're so deceiving. You can't. I can't turn them off. Nobody at UCF knows how to turn them off. But they just miss. They know nothing about our grade scheme. They don't know anything about 25 out of 25. They don't know about keep the best two, drop the lowest. None of that. Okay, so as a result, the percentages you see in web courses are like highly bogus.
Okay.
But I could tell you that having missed a few questions, how many days was that? 1 day or 2 days? How many lectures?
It was 2 days.
Okay.
Or 3.
So you're probably okay if you don't miss any more lectures.
Okay.
Okay, because for clicking for participation, you get 100% of the points, 25 out of 25, if you answer 85% of the questions.
Okay.
All right, so that means you got a 15% leeway factor that you can, burn. Okay, so for most semesters, that's 1 or 2 lectures.
Okay, but if
Maybe.
anything, I have the excuse.
Yeah, and if it gets really desperate, like if you're in the hospital again, God forbid, but if you are, then we'll maybe make adjustments and stuff.
Okay, thank you.
But so we have this now. We'll just keep it in reserve. You probably won't need it by the end of the semester. You'll still probably be able to get 25 out of 25. So
Great. Thank you
Right.
so much.
you're welcome.
Okay, so with the exam,
Question.
I know you said study the lecture notes. I was just wondering how specific, because that chart, should we know specific numbers about things?
The chart.
Or just
Oh, you
the
mean
chart
the
had
like
today?
Mars and Earth?
Should we remember specific
Um,
numbers on that?
No, don't try to memorize those numbers. Try to remember how we think about them.
Okay.
Because what I'll do on a test is I would give you that table and then ask you, interrogate you basically, and see if you can make judgment calls and make decisions based on that table.
Okay.
So I don't give a doggone if you know that the semi-major axis of Mars is 1.524 astronomical units. Big deal. I mean, did you already memorize that?
No.
No, okay. But I mean, if you memorize it, it's not like great shakes. That's not what astronomers do.
Okay.
So we're here to think, and that's actually a lot more difficult than memorizing. So I'll be giving you tables and stuff like that, typically, or images, graphs. I might give you some spectra to look at. The ones with the big spikes up or the big bullet holes down. I might give you something like that to analyze and think about and stuff. Make some decisions, some basic and some complicated decisions about it. But like you heard me say twice and three times again.
Yeah.
The lecture notes should be your study guide, and let everything else direct you back to the lecture notes. Okay, so if it supports the lecture notes, it's something, or homework or clicking,
Okay.
So, all right,
Thank you.
good.
That was basically my question. The homework.
Yeah.
Can we refer to that?
Svensk,
Yes.
yeah,
Yes.
from Sweden.
So the homework, could we use that also as a study guide? Going
Yeah,
through?
yeah, the homework is good. It's a good, so lecture notes is priority number 1.
Yes. Okay.
And then homework and clicking, priority level number 2. So you're good.
Good.
So, and the homework is pretty extensive. I mean, I pile it on you guys. I mean, you guys have a lot of stuff to do when I give you homework.
Yeah.
And so, yeah, that would form a nice mini study guide as well.
Yeah, because I didn't take like lecture notes for the first two lectures because I was like more listening to you.
Yeah.
Because that was hard to
How am I
understand
doing?
everything, but
Can you understand me pretty
Yeah.
good? Or?
now when
Have you used YouTube at all?
Yeah, a little bit.
Good.
But basically, I've just focused on homework and going through that. And like the 5 last lectures, I've been taking notes. But
Good. Do you know that you could turn on closed caption in YouTube?
how was that?
It means it's like subtitles. So
Okay,
in an American film, you can turn on Swedish subtitles, right?
all right.
And I think you can do that in YouTube.
Okay.
So that might help you too, as kind of as an extra study booster.
All right.
You know, help things study. Now, what's your name again?
Anton,
Anton. Okay, good. All right, man. Good.
thanks.
I have a question regarding alternative testing.
Hold on a second.
Okay.